Yesterday's class we discussed about the electrical measurements introduction. Okay, thank you, sir. Introduction and PMMC meter we discussed. Okay, so in PMMC meter we discussed about the how deflection torque is developing and how damping torque is developed. Okay, and controlling torque also. So we'll write some important formulas for a PMMC meter. Most probably we will get theory questions only. In case if they ask any simple problem also, we are able to solve that one. Okay, for that I am going to write some formulas here. Deflection derivation not required. Deflection torque is equal to BINA. Okay, where B is flux density, B is flux density, where is I is coil current, N is number of turns, where A is area. Okay, where A is area of the core. Okay, now controlling torque is going to be developed by spring. Screen not visible. Sorry, sir. Okay, sir. Deflection torque is given by BINA, where B is flux density, I is coil current, N is number of turns in a given coil, A is the area of the core. TC is controlling torque. Actually, the controlling torque is going to be developed by spring. So that is going to be written as Kc theta. Where theta is the
Excuse me,
tight.
sir.
Kushwan sir, any doubt?
Sir, screen is not visible, sir.
Still not visible.
Yes, sir.
Yes, sir, screen is not visible.
Okay, sir, wait a minute. Now, is it okay?
Yes, sir, visible now.
Okay, thank you. Where Kc is the spring constant, and theta is the angle of deflection. Okay, and at final position, TD is equal to TC, or you can write Kc theta equal to BINA. From this, deflection theta is given as BINA by Kc. Okay, most probably you will get a theory question only, but in case they may ask the relations. For suppose if spring constant is more, how it is going to affect our deflection, or number of turns increase, how it will. Based on the relation also you can able to get the question. That's why I given the formula. Okay, so and we discussed about the extension of range of meters in yesterday's class. We'll solve one numerical for each, so that we will understand the concept. Okay, the question is like this: 0 to 1 milliampere ammeter has its internal resistance of 4 ohms. Its range is to be extended to 100 ampere. Then the value of shunt resistance required is. What they are asking is, they given an ammeter. So whenever ammeter is given, it is going to use for measuring of current. So they given the maximum current rating of a coil is 1 milliamps. That is called full scale deflection. IFSD is called full scale deflection as 1 milliampere. And resistance, meter resistance RM as 4 ohms. Okay, its range need to be extended to 100 amps. So what they are asking, actually the coil can be carried only 1 milliampere, but we need to measure 100 amps, means we need to go for the some external arrangement that are called shunt arrangement. We already discussed in the previous class. So in previous class we written the formula R shunt is equal to Rm by m minus 1. Here m is the multiplication factor. M is given by I full scale deflection by I, where I is the measuring current. Let's take how much we need to measure, 100 amps. Just substitute the given values. Full scale deflection is 1 milliampere and full current 100. Okay, how much you will get? It's around 10 power minus 5. Rm they given us 4 ohms divided by 10 power minus 5 can be written as 100 into 10 power minus 3 minus. Okay, like that also you can write, no? It's 10 power minus 1. If 10 power minus 5 only will come. Okay, just substitute the values here. 1 milliamp they given. What is this? I by m. Sorry, the formula is like this. The formula given is I by Im. I by Im. I is 100. Im is 10 power minus 3. It will come around 10 power 5. Okay, 10 power 5. If you substitute 10 power 5 here, as 10 power 5 is a very large value, you can neglect the 1 there. Okay, so RSH approximately can be written as, what will come, 400 kilo ohms. 400 kilo ohms. This is the answer. Okay, so if you get any problems in measurements, means the chances from this type of questions is very more. That means many of the examinations.
Sir,
sir, बताइए sir, question
sir,
sir.
10 to the power minus 5 will go to upside, so it will be 10 to the power minus 5. So 400.
Oh, sorry sir. This will be 10 power minus 5 will go, means you can write 40 micro ohms.
40 microohms, yes.
Sorry sir. You can write it as 40 into 10 power minus 6. It will give 40 micro ohms. Micro ohms. Okay, sir. So RSH required is 40 micro ohms. Is correct. We'll see next question. This is related to the voltmeter. So we'll see what is the given question. A moving coil voltmeter. Actually, that PMMC is also called as simply moving coil meter. Okay, don't get confused. Permanent magnet moving coil or moving coil. In general, in common, they used to call it as moving coil. Okay, so voltmeter they given. Voltmeter means it is going to use it for measurement of voltage. So they given the maximum voltage can be measured by the meter is 20 millivolts, and the resistance Rm is given as 2 ohms. Then what they are asking, the meter need to extend up to 300 volts. Okay, by using this meter we need to measure 300 volts. For that, what we are going to do, we are going to use the series multipliers. We already discussed in the previous class. We'll just write the formula. M is equal to V by Vm. M is equal to V by Vm. And R series, RSC you can write. Series multiplier is Rm into M minus 1. Rm into M minus 1. it is 2. You can calculate m. M is 300 by Vm, how much given? 20 millivolts. Approximately how much it will come? 15. If it is go above 15 into 10 cube, we can write. Okay, 15 into 10 cube minus 1.
Sir, sound is not audible.
Oh, okay, sir. Now is it okay, sir?
No, no, sir, it is
Sound
audible.
is not
I think,
audible.
sir, I think some problem in his side only. Your voice is audible.
Okay,
Our
sir,
side
sir.
is clear, sir.
ओके ओके सर. सर कुमार सर, आप एक बार लॉग आउट करके लॉग इन कर दीजिए.
Okay, sir. Okay. Okay.
ओके ओके सर, ओके सर. So by simplifying this, we'll get around, since it is a high value, we can neglect the 1. Approximately, you can write it as 2 into 15 into 10 cube. You can write it as around 30 kilo ohms. So series multiplier required is 30 kilo ohms. Okay, is it clear? कुमार सर, अभी आवाज आ रहा है क्या? कुमार सर.
Sound is audible, sir.
Okay sir, thank you. Okay, so if
Okay.
any problem coming in the measurements, especially moving coil meter, means they will ask problems like this only. Most of the examinations, this is the repeated questions. They will give questions like directly like this, but we need to be very focus on the what are the given terms and how to substitute in a given formula. Okay, don't get confused. Wherever they are giving that millivolts range, means that is the meter values. Okay, wherever they are giving in the millivolt or milliampere range, that is the meter values. We need to take it as Vm or Im. Okay, wherever higher values are there, that means 100 amperes or 300 volts, that is going to measuring value. We are going to measure that value. That is V or I, you need to take like that. Okay, so if you are able to substitute the given values in the given formula, you will get the answer very easily. Okay, any doubt in this? कुमार सर, आप वीडियो थोड़ा बंद कर दीजिए. Okay, next instrument is moving iron instrument. Okay, one more thing what we need to discuss about moving coil meter is, or PMMC meter is, it is going to measure only DC. It is going to, it is used for only DC measurements. It is only used for DC measurements. That means DC voltage and current. DC measurements. We can't measure the AC. We already discussed in the previous session. So since it is a DC it is going to measure. This is also called as average value. Okay, don't get confused. DC measurements are average values. Average values. In networks, we are going to study about what is mean by average value and what is mean by RMS value. For time being, just remember DC values are equal to the average values. Okay, so our PMMC meter is only used for DC measurements such as DC voltage and DC current. This is also called as average values. Okay, so in order to measure the AC values, that means AC voltage and AC currents, we are going to use moving iron instruments. Okay, moving iron instruments, the name itself it is telling moving iron. One small iron piece is going to be moved in a given magnetic field, thereby it is going to developing the deflecting torque. Okay, in the previous class I already explained what are the three things we are need to focus in a given instrument is deflecting torque, controlling torque and damping torque. How these are going to be developed, if you understand this, we can able to explain the operation of a given instrument. First see, there is a coil. Okay, the first one is coil. By using coil, we are going to develop the magnetic field. Okay, by wounding a coil on the iron core, we developed the magnetic field. The flux is developed. Now what we are going to do, this is the small iron piece. This is the small iron piece. We know that iron is a good good metal which will attract to the magnetic field very quickly. Okay, you might have seen in the laboratories also. Now what will happen, whatever the magnetic field is created here, that is going to attract the this small iron piece. The small iron piece is going to be attracted by the magnetic field created by measuring quantity. Okay, measuring quantity means, for suppose we are going to measure a current. Let's take a current. How we are going to connect like this? The current is flowing through like this and returning like this. Because of this, what is happening? Flux is created and magnetic field is created. This magnetic energy will attract this iron piece. Okay, whenever iron piece is attracted, during this process, some torque will develop. This torque is nothing but deflecting torque. Thereby, the pointer will start moving. Thereby, the pointer starts moving. Okay, this type of instrument is called attracting type. This type of instrument is called MI attractive type instrument. Attractive type. Attractive type instrument. Actually, in MI instrument, two types are there: attractive type and repulsive type. Attractive and repulsive. Repulsive type. What is meant by attractive means attracting the iron piece. In repulsive means repulsive force will occur and it will exert a force on the iron piece, and the iron piece will move away from the magnetic field. Okay, that is going to discuss in the coming slide. For timing, just remember, in attractive type instrument, so whatever the measuring quantity, I am going to measure here current. With that current, we develop the magnetic field. This magnetic field will attract the iron piece. Whenever iron piece is moving, thereby the pointer also will moving here. Okay, the pointer also is going to move. Thereby we will getting the deflection. Thereby we will get the deflection. This is about deflection torque. Next, coming to controlling torque. The controlling torque, here also we are going to use spring control only. Okay, I didn't shown here in the picture, but here also we are going to use the spring control for controlling torque. Now coming to damping torque, this is important. T damping. The damping torque you are going to develop by using air friction damping. Air friction damping. Air friction damping. In this moving iron instrument, we are going to use air friction damping. By seeing this picture itself, we can imagine that whenever this pointer is moving, the piston is going to be pushed inside the tank. Okay, pushed inside the tank. It is just like our cycle pump. Okay, it is just like our cycle pump. Why you are using air friction damping in moving iron means, whatever you are using here, it is a electromagnet. Reason why you are using air friction damping here is electromagnet is weaker than permanent magnet. Weaker than permanent magnet. If we use eddy current damping, the main reading may get disturbed. The main reading may get, or main deflection may get disturbed. What I mean to say here is, in PMMC meter, the magnetic field is created by permanent magnet. Okay, since permanent magnet is having more strength as compared to the electromagnetic. Okay, so electromagnet is weaker when you compare with the permanent magnet. Okay, in that case, if you are using eddy current damping in electromagnet, this is going to influence the deflection of the meter. Okay, it is going to influence the deflection of the meter. That's why wherever electromagnet principle you are using, there air friction, there we are going to use air friction damping. There we are not going to use eddy current damping. Is it clear? Okay. So what we need to remember, in moving iron instrument, deflection torque is going to developed by measuring quantity, controlling torque is going to developed by spring mechanism, and third one, damping torque is developed by air friction damping. Here we are not using eddy current damping because electromagnet is weaker than the permanent magnet. If you are going to use the eddy current damping, it may affect the final reading of the instrument. Okay.
Sir, please repeat, sir. The
कुशवंत सर, आपका क्या डाउट है डैम्पिंग टार्क में?
no, sir, no doubt, sir. You just tell the T deflection is developed by.
Okay, sir. You are going to noting the things,
Yeah.
sir.
Yes, sir.
Yes, sir. Sure. I will repeat, sir. Deflection torque is developed by measuring quantity. That means if you are using, if you are going to use as an ammeter, current is the measuring quantity. With the help of current, the deflecting torque is going to be developed. Whereas a controlling torque is developed by spring mechanism. Damping torque is going to be developed by air friction damping.
Okay, thank you, sir.
Okay, sir. So whatever you see, that is attractive type. Now we are going to see repulsive type. Repulsive type. Repulsive type moving iron instrument. This is repulsive type. What is repulsive means? Here two plates will be there. One is fixed plate and in moving iron moving plate. Okay. If you see here, this is fixed one and this is moving one. I marked in the picture. Okay. What is happening? Here we are going to make two magnets. Okay. We are going to make two magnets. So whatever the force going to develop here is repulsive type force is going to be made. Okay, that with the help of this repulsive force, we are going to move the pointer. Okay, with the help of this repulsive force, we are going to move the pointer. We are going to develop the deflecting torque. Okay, how it is going to happen means, the winding, we are going to wound the coil inside the machine such that the fixed plate will going to form as, let's take north pole, and this moving iron pass. Okay, this is going to form as this also north pole. That means same poles are going to formed. Okay, same poles are going to formed. Since these two are same poles, there exists a repulsive force. Okay, because of this repulsive force, the iron piece will move inside the instrument. Okay, whenever it starts deflecting, then deflecting with the help of deflecting torque only, the pointer is going to show the reading. Okay, so except this remaining controlling torque also same, we are going to develop by using spring mechanism. Damping torque also we are going to develop by using air friction damping. Okay, so only principle is different. In compared to attractive type, here two plates are there. These two, between these two plates, we are going to make repulsive force. We are going to develop the repulsive force by using the measuring quantity. That means if you are going to measure current, with the help of current, we are going to make this repulsive force such that the pointer is moving. Okay, so we will write some relations here. Deflecting torque is actually, we can given as half I square dl by d theta, where L is the inductance of the coil. Okay, in the networks we will study about the inductance, what is mean by inductor and what is mean by inductance in detail. For time being, just remember, wherever we are having a iron piece and we are winding a wire on it. Okay, wherever we are having a iron, we are having an iron piece and we are wounding a wire on it. This is called coil. This is called coil. It is having some property called inductance. It is having some property called inductance. It is indicated by L. Okay, so we are going to study in detail in the network subject. For just time being, you just remember, wherever a coil is there and we are exciting with AC supply, it is going to offered some value that is called inductance. Okay, where L is the inductance of the coil, we will write here. I is current carried by the coil. Current carried by the coil. L is inductance of the coil. Inductance of the coil. Where theta is deflection. Theta is deflection. Deflection angle you can write. Okay. And we know controlling torque is developed by Kc theta. At final value, at final steady state value, Tc is equal to Td. That implies theta can be written as half I square by Kc into dl by d theta. Okay. From this formula, what we need to remember here also, we mostly won't get any problem, but the relation is important. The deflection of the pointer is directly proportional to I square. This is important point. Okay. If you observe in the PMMC meter, their deflection theta is directly proportional to current. That means whatever the measuring quantity is there, that is directly proportional there. But here, if you see, it is not not directly proportional to I. It is directly proportional to square of the current. Okay. Since it is a square of the current, the scale in moving iron instrument is non-uniform scale. Non-uniform scale will be there. Non-uniform scale. Why? Because why non-uniform scale means because theta is directly proportional to I square. This is important for our exam. Okay. Whereas in moving coil instruments, theta is directly proportional to I. So there we will get uniform scale. You can observe the differences easily. See, from 5 to 10, how many codes are there? From 10 to 15, how many codes are there? Okay. The scale is not uniform in moving iron instrument. Whereas in moving coil instrument, if you see all the codes are equal. Okay, all codes are equal. That means the distance from 0 to 200, how much is there? Same will be there for 200 to 400, like that. Okay. Here in PMMC meter, the scale is uniform because the theta is directly proportional to I. Whereas in moving iron instrument, the scale is non-uniform because theta is directly proportional to I square. Okay. So now we'll write some important factors related to moving iron instrument. It is used to measure only AC. It is used to measure AC values. AC voltage or current. AC voltage or current values. Or that also called as RMS value. RMS values. Okay. In PMMC meter, that is going to measure for DC values and average values. This is RMS value for AC. By using this meter, you can measure DC also. Okay, not only AC, you can measure DC also. But the problem is, compared to moving coil instrument, moving iron instruments having some drawbacks. That means more power loss will be there. We are going to discuss in the coming session. We'll compare moving coil and moving iron. Just for timing, you remember, moving iron instrument can be used for both AC as well as DC measurements. But it is more efficient for AC than DC. So that's why moving iron instrument is limited up to only AC measurements. It is not used for DC measurement. If you want, you can measure, but it is having some drawbacks if you are going to measure the DC values. Okay, that's why we are going to use moving iron only for AC and PMMC for DC. Okay, next type is EMMC meter. This is called electromagnet moving coil meter. We can write also it as electromagnet moving coil meter. moving coil meter. Electromagnet moving coil meter. Okay, that is also called as dynamometer type or electrodynamometer type. Electrodynamometer type. The other name for this meter is electrodynamometer or EMMC meter. Okay, both are same only. So here we are going to use air core. We are going to use air core. Air core means we are not using the actually in transformers. If you see, we are using the iron that is silicon core. We are used, okay, for providing the path for the flux. But in a dynamometer type, we are going to use the air core. Air core means this is not a magnetic material. Okay, for supporting winding, whatever the material you are using, this is not a magnetic material. It is not a non-magnetic material. Non-magnetic material you are going to use. Why you are using non-magnetic material means to reduce the errors in meter. I am going to discuss in the last slide. Okay, for time being, just remember in AMMC meter we are going to use the air core to minimize the errors. कुमार सर आपका कुछ डाउट है क्या? Okay, so this instrument is also called as transfer instrument. This instrument is also called as transfer instrument. Why it is called transfer instrument means it can able to measure both AC and DC. Measure both AC and DC. That means we discussed moving iron also measuring both AC and DC. But for moving iron meter, for DC measurements, there are more errors are occurring. So that's why that is not suitable for DC measurements. But in case of dynamometer type meter, what is happening? It will give same error. That means actually even though you take many precautions while designing the meter, there exists some errors. Okay, there exists some errors. So this instrument will give same error for AC measurement as well as DC measurement. That's why this instrument is called transfer instrument. We can able to measure both AC as well as DC quantities or DC values. Okay, here if you observe, there are two magnets are forming. That means there are two coils are there. This is called current coil or in short form CC. One more coil is there. This is called pressure coil or PC. Okay, we are having two coils CC and PC. Okay, we can able to use this meter as ammeter or voltmeter or wattmeter also. Wattmeter means to measure power. Wattmeter is used to measure power. Okay, but in general we are going to use a dynamometer type for usually only for measurement of power. In general, I am telling. If you want, you can measure as you can use it as a ammeter also. You can use it as a voltmeter also. But in general, for our application wise, we are going to use wattmeter. Dynamometer type instrument is used for wattmeter only. Okay, this is also very important for our exam. Is it clear? Coming to torques, we will see what are the different torques are occurring. The torque is first one is deflecting torque. Deflecting torque is same. That means whatever the measuring quantity is there, the same quantity is going to cause the deflecting torque. Next, controlling torque is going to be developed by spring mechanism. Okay, the controlling torque is developed by spring Kc theta. And since Since it is you are using we are using electromagnet, eddy current damping is not used. No, we are not going to use eddy current damping here. Okay, here also we are going to use air friction damping. Air friction damping. The damping torque is developed by air friction mechanism, and controlling torque by spring mechanism, and deflecting torque by measuring quantity. Okay, this instrument can be used as ammeter, voltmeter, as well as wattmeter. But in general, we are going to prefer for measuring of power, that is wattmeter. Okay, this I summarize the different formulas related to different instruments. PMMC, moving iron, and dynamometer or EMMC, both are same. The formulas are like this: deflecting torque and deflection. Where Kc is the spring constant and M is the mutual inductance. And here if you see pi is the angle between I1 and I2. Angle between I1 and I2, where I1 is the current in current coil, current in CC. I2 is the current in PC. PC is pressure coil. Okay. Actually, for our exam point of view, relations are important. Okay. So the deflection is directly proportional to both I1 and I2. Okay. For our exam point of view, we need to just remember the formulas. Okay. We may get one or two, mostly we may get conceptual questions only on this topic. In this picture, we can see how we are going to use it as a ammeter and voltmeter. First, we will see by ammeter how we are going to use.
Sir,
See,
previous slide, please.
1 minute, sir.
Okay, sir. Thank you.
Okay, sir. Okay, these are the different connections how we are going to use for the ammeter, voltmeter, and wattmeter. Okay, just see here. This is CC. This is CCR current coil. This is moving coil, also called as pressure coil. You can say PCR moving coil. Okay. So this is the connection. Since this is the load and this is the supply. So since you connected in series, whatever the current is flowing in the load, same current will flow through here. Okay. Thereby we are satisfying the ammeter condition, and we can measure the current. Second one, if you see, this is the voltmeter. Okay, this is the voltmeter. How we are going to use voltmeter? This is the load voltage. Let's take this is load, and the connection will be like this. So fixed coils or current coils are same, moving coil or pressure coil is same. Okay. And one more diagram is about wattmeter. This is important. Okay. Dynamometer type, we are going to use it as a wattmeter. If you see here, there are three terminals are important. This is M, this is C, this is C, this is L, and this is V. These are the wattmeter terminals. I think if in our laboratories and all, you might have seen the wattmeter connection, or you might have done the experiment on wattmeter. There you might have seen the terminals M, C, L, V. What it means where M indicates mains. Mains means supply. Mains means where we are giving main supply. Okay. M is mains. C is common. Where L is line, load or line. Actually, line we will say In general, line is nothing but load side. Also, you can say line or load. You can say it as load. Load, and V is voltage. V is voltage. Okay, sir. For this connection, terminals are important, sir. Actually, 1 or 2 exams they given this diagram, and they asked about what is mean by M, what is mean by C, and what is mean by L. They asked about the terminals. You may get the theory question from this. Okay. So in wattmeter connection, what is going to happen? This moving coil is going to give the voltage, and fixed coils is going to measure the current. Thereby, power is nothing but VI cos pi. Power is nothing but VI cos pi. Okay, where pi is the angle between V and I. Where pi is angle between V and I. We are going to measure the power by using wattmeter. Okay, this V is going to be measured by moving coil, and this is going to measured by current coil. Okay, so for our exam point of view, this theory concept is important. Different types of errors in meters. Till now we discussed PMMC, moving iron, and moving coil. Okay, first I will explain what is mean by frictional error, and we'll compare the error in moving iron, how it will be in moving coil, and how it will be moving iron, and how it will be in dynamometer. Okay, this is important for our exam. Okay, first thing is frictional error. Frictional error means, what is mean by frictional error means, wherever moving parts are there, there exists some friction. Okay, there some amount of energy is going to be wasted. One thing we need to remember is, whatever the meters we are going to use for measurement, this should not disturb the existing circuit. For suppose, let's take an example. I need to measure the current in a one light load. I am having one light load. I need to measure what is the current taken by light load. Okay, this is the existing circuit. If you are going to connect any external instrument for measuring purpose, that should not disturb the circuit parameters. That means circuit parameters like voltage or current, or it should not disturb the load also. Okay, so for measuring current, what we need to do, we need to connect ammeter in series with the load like this. So whatever the current is flowing here, same current will flow through the ammeter also. So, okay, so that's why it is called series connection. Now we satisfied the series connection for measuring the current. But the thing is, so whenever this current is flowing inside this, there exists some losses. Okay, because of some losses, it will show some error. Okay, what is the error? Error is nothing but true value minus measured value. Let's take this light load is taking some current of 5 amperes. Actually, it is taking 5 amperes. After connecting ammeter, if it is a ideal ammeter, it has to show 5 amperes. If it is a ideal ammeter, ideal means it is not having any losses, and it is not having any defects inside that. Okay, if you assume that conditions, then our ammeter is going to show 5 amperes. But because of some losses occurring, some amount of energy is wasted in the meter, what is going to happen? This ammeter will show 4 amps only. In practical condition, this ammeter is going to show 4 amps only. So the error will be, how much error will get? Error will be 1 ampere. Okay, so from this what we understood, even though you've taken many precautions while designing the meter, it is having some losses. It has to meet some losses. Because of this, it is not able to show the accurate value. 100% accurate, it can't able to show. It is having some amount of error. Okay, it will show some error. We will see what are the different errors are going to be occurred in the given instrument. First one is frictional error. Wherever moving parts are there, if you see all 3 meters, there exists some moving mechanism, no? So wherever moving parts are there, there exists some friction. Because of this friction, some amount of energy is going to be wasted. This frictional error is directly proportional to the torque by weight ratio. That means not directly proportional. We'll say like this: frictional error is inversely proportional to the torque to weight ratio. Okay, inversely proportional to the torque to weight ratio. What is mean by torque to weight ratio means, for developing of, let's take some 10 Newton meters, for developing of torque 10 Newton meters, which instrument weight is very less, that instrument will have the less friction losses. What it indicates, torque, from this what I can say, torque weight to weight ratio should be very high. For a given instrument, if torque to weight ratio is very high, then frictional error is going to be less. Okay. What is mean by torque to weight ratio means, for a given torque, the weight of the moving system should be as low as possible. Okay, the ratio high means weight should be low. That means in a given instrument, for the same developing torque, if the weight of the moving system is less, then that instrument is having less frictional error. This instrument is having less frictional error. We'll make a table here for different type of instruments. We'll compare. First one is PMMC. Second one is moving iron. Third one is EMMC or dynamometer. First error is frictional error. Frictional error. Okay, if you see here, the weight of the moving mechanism, if you see, here, this is the PMMC. It is having coil and frame, and here some jewel bearings will be there. That means at bottom some bearing mechanism will be there. Here some, for smooth rotation of this rod, some bearing mechanism will be there. Jewel bearings, like that they used to tell. Okay. Here actually some friction will occur. Some amount of energy is going to be wasted. If you see here, the weight is more. The weight is more in PMMC as compared to the moving iron. Here if you see, only the weight is only the iron piece weight only will come in the moving mechanism. Okay. So, and if you see dynamometer type, here also the coil weight is more. So in overall, if you compare, this frictional error is more here. Frictional error is more in moving PMMC and less in moving iron. Here also more. Frictional error is more than the PMMC, and moving iron. Why? Because in a dynamometer type, we are having more weight in the moving mechanism. Okay, that is about frictional error. We'll see other error is temperature error. This is also important for our examination point of view. Many of the exams it is repeated. Okay, what is mean by temperature error means, since our meters is carrying current. Let's take this example. Since our meter is carrying current, especially in PMMC meter, what is happening? The current is flowing through the springs. So the springs will get heated. Okay, whenever current is flowing through the springs, the spring will get heated up. Because of the heat, there is a chance of elongation of the spring. Okay, there is a chance of elongation of the spring. You might have seen, whenever you heat the spring, it will lose its ability. That means it is going to be elongated. Because of this elongation, it is going to affect the controlling torque. Okay, it is going to affect the controlling torque. So we already discussed in the previous session, the controlling torque is going to play the crucial role for getting the final deflection. Because of this temperature, it is going to affect in the controlling torque. Thereby some error going to be occurred. This error is called temperature error. This is going to be occurred in only PMMC meter, that too in ammeter. Temperature will be occurred only in PMMC, sorry, PMMC ammeter. Why only ammeter, not voltmeter? Means in ammeter only the meter is going to carry more current. In voltmeter, we are going to connect across the voltage. That means, for suppose if you want to measure the voltage here, what you are going to do? We are going to connect voltmeter across the meter. Okay, we already discussed, whenever you are connecting external instrument, it should not affect the circuit conditions. That means whatever the current is taken by the load, same current need to flow by connect. Even though you connected the voltmeter, same current need to flow. That means whatever the current flow through the voltmeter IV is as low as possible, then only you can able to maintain the circuit conditions same. Otherwise, what will happen? If the voltmeter draws more current, means the load current is going to be disturbed here. So as per our discussion, whatever the meters you are going to connect, that should not affect the circuit parameters. That means current and voltage, it should not affect. Okay, so for that we need to design our meter such that it should draw the very low current. Okay, that's why voltmeter is drawing very less low current, so the temperature rise in voltmeter is less, so there the spring elongation is less in if you are using as a voltmeter. So the temperature error is more in PMMC ammeter. This is going to be overcome by connecting swamping resistance. This is important and repeated many times. Reduced uh, reduced by connecting swamping resistance. Yes, swamping resistance in series with the ammeter. In series with the meter. Okay, this is very very important, sir. It is repeated many examinations. Swamping resistance. What is meant by swamping resistance? Means the resistance is independent of temperature. That means that resistance is prepared with the help of some material that is called phosphor bronze. Mostly we used to say phosphor bronze. The material you are going to hear is phosphor bronze. Phosphor bronze material you are going to use. It is independent of the temperature. Okay, it is independent of the temperature. Even though temperature is increased, the resistance won't be affected. Okay, to overcome the temperature error, we are going to use swamping resistance in PMMC ammeter. Okay, PMMC ammeter. Now we'll see what is that temperature error. So it is more in PMMC. Here less moving iron, it is less, and here it is more than PMMC. Why? Because here we are using two coils. Okay, here we are using two coils, so heat developed is more as compared to the moving coil. Okay, next error is stray magnetic field error. What is mean by stray magnetic field error? Means, okay, we are having a instrument. Let's take ammeter is there with us. We have ammeter. We went to the laboratory. Nearby laboratory, one big permanent magnet motor is there. Okay, whenever you went to near to the permanent magnet meter, what is happen? This strength is more. Strength of this permanent magnet is more. Okay, because of this is going to affect the deflection in the ammeter. Okay, the external magnetic field is going to affect the deflection in a given instrument. Then that magnetic field is called stray magnetic field, and because of this, it is going to affect the final reading of a given instrument. Okay, sir. So what is mean by stray magnetic field? Means the external magnetic field in surroundings of a given instrument. Okay, stray magnetic field. What is meant by stray magnetic field means external 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 magnetic field surrounding by the meter, surrounding by the meter, surrounding by the meter. Okay, so this effect is more in moving iron and EMMC. Why? These two are electromagnets. That's why these are weaker than the permanent magnets. But in PMMC we are using the permanent magnet. That's why this error is less in PMMC. This error is less in PMMC, but more in moving iron and EMMC. For that, what we are going to do to overcome this? How we are going to overcome means we are going to, by providing iron shield, by providing iron shield, by providing iron shield, this error can be minimized. This error can be minimized. This error can be minimized. Is it clear, sir? This is also important for our exam. Okay. By what is meant by stray magnetic field? Stray magnetic field means external magnetic field which is surrounded by our meter. That is called stray magnetic field. The error due to this magnetic field can be minimized by providing iron shield for a given meter. Okay. Next error is about frequency error. Next error is about frequency error. What is meant by frequency error means for a same quantity, if the frequency of the quantity is changing, frequency error. Let's take AC supply. Let's take AC supply. Normally, in general, AC voltage, if you take a single phase AC voltage, it will be 230 volts and 50 hertz. In general, it will be like this. Okay, but in our telecommunication equipments, what is happening? The frequency is going to be varied. That means it may be in kilohertz or even megahertz also it will go. Okay, the same voltage with different frequencies, what is going to happen? The reading also will be different. Okay, the reading of the meter is going to be varied. Reading of meter will going to vary at different frequencies, going to vary at different frequencies. This error is called frequency error. This error is called frequency error. Okay, especially this is occurring in moving iron instrument. Okay, where we are using for different frequency measurements, this frequency error will going to occur. That's why moving iron instrument we'll write here. First thing is moving coil, moving iron, and EMMC. Since you are going to measure DC for PMMC, this is going to be 0. The error due to frequency is 0 in moving coil, but here it is more. But here it is more. But in EMMC, if you are using for watt meter, if you are using for watt meter, it is low. If you are using for if you are using EMMC meter as watt meter, error is low. Error is low. But if you are going to use as ammeter or voltmeter, error is more. Error is high. Error is high. That's why this dynamometer is going to be used only for watt meter application instead of ammeter or voltmeter. And because of this frequency error, it is going to limit it up to 125 hertz. Okay, this moving iron instrument for measurement of AC is limited up to 125 hertz. Limited up to 125 hertz. Because of this frequency error, this moving iron instrument is limited up to 125 hertz. Okay. Next error is hysteresis error and eddy current error. Hysteresis error and eddy current error. We'll take one slide up there. Hysteresis error hysteresis error, eddy current error, eddy current error. We discussed already in machines wherever frequent magnetization and demagnetization occurring, there hysteresis hysteresis loss will be occurring. Because of hysteresis loss means some amount of energy is going to be wasted. Because of that wasted energy, the meter is going to show some less deflection. That means there exists some error. Whatever the error due to hysteresis loss, that error is called hysteresis error. Whatever the error due to eddy current loss, that is eddy current error. We will compare with different instruments, moving coil and moving iron and EMMC. Actually, hysteresis error will be very less in a moving coil, very less in a moving coil. Is very high in a moving iron, very high in a moving iron. This also very less, this is very high. Eddy current loss also very high. EMMC meter, it is 0. Why it is 0? Since we used, since air core is used, we can write it as air core is used. Because of this application, air core is used, the eddy current and hysteresis error are both are 0 for EMMC or dynamometer type meter, whereas these two errors are very high for moving iron instruments. Because of this only, moving iron is preferred only for AC measurements, not for DC measurements. Okay, so it's clear. To minimize this hysteresis error, we are going to use nickel iron. We are going to use nickel iron core for moving iron instruments. Okay, to minimize this, to reduce this, to decrease this, nickel iron core is going to be used for moving iron instrument. Okay, this eddy current losses are normally directly proportional to frequency. Okay, this is directly proportional to frequency. So this here also we are going to limit up to 125 hertz for moving iron instruments. Up to 125 hertz we are limiting for measurement of the voltage. Why means because since eddy current losses are going to increase square of the frequency. If you are going for higher frequencies, the losses are more, the error due to eddy currents is going to be high. That's why this moving iron instrument is limited up to 125 hertz only. Okay, is it clear? Next, one more important thing is wattmeter connections. We already seen the how wattmeter is going to connect in a given circuit. Let's see the possibility that there are two possibilities of connecting a moving coil. Okay, the wattmeter connection we've seen, that means wattmeter is used for measurement of power. In that wattmeter, two coils are there, fixed coil or moving coil, or current coil or pressure coil. We can call it as current coil or fixed coil, moving coil or pressure coil. Okay, there are two possibilities of connections in wattmeter. If you see here, this we discussed about MLC terminals. MLC terminals. MLC terminals means M means mains, C is common, L means load, V means voltage. Where you are going to connect this pressure coil, based on that, this connection is named MC connection and LC connection. You can observe the difference how the pressure coil is connected from figure 1 to figure 2. Okay, so there are two possibilities are there for connecting a wattmeter for measuring the power. Okay, in both cases error is there. Why error means this current coil is need to measure the current, voltage coil is need to measure the load voltage, but what is happening, along with the load current. This current coil also drawing some current. Okay, for current coil also taking some amount of current for production of magnetic field. Okay, that means some amount of current is going to be wasted here. Okay, some amount of current is going to be wasted here in the term of loss. In the form of loss, I square R loss is going to occur in the current coil. Okay, so this power is going to be wasted in current coil. This is going to be making some error in the measurement. Actually, the load is, let's take it is measuring 100, load is taking 100 watts, but if you connect our wattmeter, because of the wattmeter connection, it is indicating along with 100 watts, and whatever the power loss, let's take it is some 10 watts, whatever the power loss occurring in the current coil also it is measuring. So total power measuring as 110 watts. It has to measure as 100 watts, but because of this type of connection, it is going to measuring as 110 watts. So some error is there in this connection, error is there. How the error is can be minimized? The error is minimized if load current is small. That means this MC connection is preferred wherever you are going to use for low loads. That means wherever load current is less, there we can prefer MC connection. If load current is more, means I square R loss in current coil is also more. Okay, because of this error also will be high. That's why MC connection is preferred for low load current or small load current. This is important. We make a theory question, that's why I am explaining this. MC connection is preferred for low load currents. Coming to LC connection, in LC connection what is happening, this pressure coil need to measure the voltage across the load, but what is happening, it is drawing some current I2. Okay, it is drawing some current I2, and it is since the coil is having some winding, the pressure coil is having more number of turns. Actually pressure coil will have more turns than more number of turns more number of turns than current coil. Whenever more number of turns there, resistance also will be high. Okay, resistance also will be high. Here also some power loss is going to occur, V square by R. Okay, in pressure coil also some power is going to be wasted. Because of this, error will occur. This error can be minimized when error is minimum if load current is high. Okay, if whenever load current is high, we are going to prefer LC connection. Wherever load current is less, we are going to prefer MC connection. Is it clear? You may get any theory question, that's why I'm focusing on that concept. Okay, one more important thing is low power factor meter. Actually in wattmeter there are two types are there. In
Sir,
wattmeter
previous
there
slide, sir.
are 1 minute, sir. Okay, sir.
Thank you, sir. Thank you.
Now is it okay, sir?
Sir, thank you.
Okay, sir. Okay, wattmeter means we know power is equal to P is equal to VI cos pi, where cos pi is called power factor. Cos pi is called power factor. Actually, based on the power factor, we used to have unity power factor or upper power factor, you can say. That is called UPF, upper power factor or unity power factor, or lower power factor or LPF meter. LPF meter and UPF meter. How we classified means based on the power factor cos pi. Okay. In while I am explaining the open circuit test of the transformer, open circuit test of this transformer, what I told, the power factor of the power factor is very less. That's why you are going to use the LPF. From the formula of this dynamometer, TD is directly proportional to I1 I2 cos pi. I1 I2 cos pi. If cos pi is low means what will happen? Deflection torque also will be less. Okay, deflection torque also will be less. Okay, normal wattmeter if you use for low power factor measurements, we can't measure the accurate value. Why? Because for low power factors, the deflection torque is less. It is not able to develop sufficient torque for deflection of the meter. Okay, that's why one special design they are going to use. The special design they are going to use. The special construction is like this. The special construction is like this. How it will be? So if you see the formula, TD is directly proportional to I1 I2, where I is the current in current coil, I2 is the current in PC pressure coil. You can this formula can be rewritten as TD is directly proportional to V by RS, V by RS, I1 cos pi. This is the V. This is V. Okay. If RS is, if you increase the, that means if you decrease the RS, then TD will increase. Okay. If you decrease the RS, TD will increase. For that, we made one arrangement like this. We made arrangement like this, and to reduce the RS, we connected a capacitor across it, and this capacitor value can be written as LP by RS square. LP by RS square. This is important for our exam point of view. In low power factor meter, what is the CC? CC is equal to LP by RS square, where LP is the inductance of pressure coil. LP is inductance of pressure coil. Inductance of pressure coil. Okay. Why LPF is separately designed means if you are going to measure the low power factor meter, the deflection torque will be very less. So we can't measure a normal wattmeter for low power factor conditions. Okay. So for that we made some design changes such that it can able to measure the low power factor values effectively. Applications, if you see, where you are going to use this low power factor meter means in OC test of transformer. OC test of transformer. OC test means open circuit test. Okay. In OC test of transformer, we are going to use low power factor type wattmeter. Okay. Till now, whatever we discussed, these all are single phase loads. Now we are going to see three phase power measurement. Okay, three phase power measurement. Before going to three phase power measurement, just have a quick recap of three phase system. Three phase system means three phase system. In networks, you are going to study, but for time being, just for making understanding, I am writing this one. Three phase system, there are two voltages will be there: line voltage, phase voltage. These are the different terminologies coming in three phase system: line voltage, phase voltage, and balanced, unbalanced. These are the next three wire system, four wire system. These are the different terminologies we are going to use in three-phase system. What is meant by line voltage means we know in three-phase system there are three phases R, Y, B. If the voltage between R and Y, if the voltage between R and Y is called line voltage. If you are measuring voltage between R phase and Y phase, between two lines, actually the three-phase system is like this. I shown here. You can see from this figure. If you are measuring voltage between R phase and Y phase, or between two lines, R line and Y line, this voltage is called line voltage. Whereas phase voltage means VRN, where N is neutral. Where N is neutral. R phase with neutral, if you are measuring, that voltage is called phase voltage. Balanced means this VRN equal to VY1 equal to VBN. If all three phase voltages are equal, then that system is called balanced system. Then same current will flow. Then IR equal to IY is equal to IB. In three phases, same current will flow. That system is called balanced system. Unbalanced means that means IR, I can write it as IR plus IY plus IN. IB is not equal to 0. Here it is 0. The sum will be, since all are phases equal, this phasor sum if you do, the net current is 0 in balanced system. Here the balance in unbalanced system it is not 0. One more is a three-wire
Excuse me,
system.
sir. Excuse me,
Sir.
sir. Explain, sir, phase voltage again.
A phase voltage, sir. If you measure the voltage between, let's take this is the neutral, sir. If you measuring
Yeah,
the
right.
voltage between R phase and neutral point, if you measuring the voltage between R phase and neutral point, that voltage is called phase voltage. If you are measuring the voltage between R phase to Y or B phase, okay, any other phase if you are measuring, then that voltage is called line voltage, sir.
Yeah, that's understand. But phase voltage is the neutral. But in a star connection or in a delta connection, a star connection, neutral
Hmm.
point.
Yes, sir.
So in any color, like red color, red or blue or yellow, anyone.
Yes, sir. Anyone if you take with respect to neutral, if you measure, that voltage is
Yeah,
called phase voltage.
yeah, right.
Okay, sir. Okay,
Okay.
sir. Okay. Three-wire system means if neutral not present, then that system is called three-wire system. If neutral not see, here it is neutral is available. If neutral is available, that system is called four-wire system, three-phase four-wire system. If if neutral is available, if neutral is available, that system is called four-wire system. Actually, in general, in delta connection, we are not having any neutral. That system is called three-wire system. In general,
Sir,
sir,
sir, in unbalanced condition, what is the value of VRN, VYN, and VBN?
that also not equal, sir. VRN not equal. Sorry, VRN not equal to VBN, not VYN not equal to VBN. So voltages phase. Actually, these are phasors, sir, not magnitudes. These are phasors. That means phasors means it is having magnitude as well as some angle will be there. In networks, we are going to study in detail. Just for time being, remember the phasors. Whatever we are discussing here, this sum also phasor sum. IR plus IY plus IB. Kushwan sir, any doubt?
Yes, sir. Yes, sir. Got it.
Okay, sir. Thank you. Okay, I think now it's clear. We are having some basic idea of a three-phase system. Okay, we are going to study in detail in the network subject. For time being, just remember what is meant by line voltage, what is meant by phase voltage, and what is meant by balanced system, unbalanced system, and three-wire system and four-wire system. These are the different terminologies in a three-phase system. If you see here, you need to measure power in three-phase system means first we need to see whether the system is 3-phase 4-wire system or 3-phase 3-wire system. What is meant by 3-phase 4-wire system? It is neutral is available, N is available. That is star connection. We are going to use star connection load. Wherever neutral is available means that connection is called star connection. In that again two conditions are coming. Whether it is balanced or unbalanced. Okay, whether it is balanced or unbalanced. Similarly, 3-phase 3-wire means here neutral not available. Neutral not available. Neutral not available. This connection is called delta connection. Delta connection. Now, if you see how many meters are required for measuring the power. For single phase measurement, 1 wattmeter is sufficient. But for measurement of 3-phase power, how many meters are required? We are going to see from this table. This is very, very important, sir. Many of the examinations, it is repeated. That
Yeah,
means,
right.
yes, sir. For balanced 3-phase system, how many wattmeters are required for measurement of power?
Two,
That
sir.
means-
2 wattmeter.
No, sir. For balanced system 1, sir. Balanced system 1, unbalanced system 2.
Okay.
Why
I mean,
1
that
meter
is
is sufficient? Why
Yeah.
1 meter is sufficient means in balanced system, voltage, current in all phases are equal. If you are measuring single phase voltage and single phase current, that is sufficient. If you multiply with the 3, we will get the total power. Okay.
Yeah, right.
Whereas in unbalanced system, each phase and each phase voltage and currents are different, so we can't able to measure with single wattmeter. But
Last
we
time
can
question
able
has
to.
came.
Yes, sir.
Last
It
time
is
question has
important, sir.
came.
Yes, sir. Yes, sir. Yes, sir. That's why this is important, sir. Don't get confused, sir. Balanced
Yeah.
system means all phase voltages and currents are equal. If you are measuring
Correct.
any one phase voltage, one phase current, if you are measuring one phase power means that is sufficient. By multiplying 3, we will get the total power in the 3-phase system. But in unbalanced condition, we are not able to calculate the power with the help of single phase power. Okay.
But
For
the
that
last,
we need.
but the last time the question was mentioned, not mentioned in balanced or unbalanced.
Okay. What is the
Whatever the
question, sir?
question
I
has
didn't.
given, question has given, not 2-phase, whatever the say 3-phase wire, 3-phase measurement of how many wattmeters would be needed.
Okay,
Answer
sir.
has
That
given
time,
2 wattmeter, neither balanced nor unbalanced.
yes, sir. If they didn't mention anything, means we need to consider unbalanced only. In
Yes, right.
general, our
That's why answer has given 2 wattmeter.
yes, sir. Yes, sir. In general,
Yeah.
if they didn't mention anything, means we need to consider it as a unbalanced only. If they
Yeah, right.
specifically mentioned as a balanced, then minimum wattmeters are 1, sir. With 1
Yeah,
meter
right.
itself, we can able to do. So that's why
Yeah,
this
yeah.
is a very, very important, sir.
Yes.
Okay.
Yes. Okay.
By using 2 wattmeters, we are going to measure the 3-phase power by using this type of connection. If you are able to connect the wattmeter like this, that means this volt V is going to be 1 phase. We need to connect 1 wattmeter like this. In other phase, we need to make B as common or any other phase as common. Okay, any other phase as common. And if we connect the wattmeter like this, then we will get the 3-phase power. We will get the 3-phase power. We'll see the some basic calculations here that are important.
Sir,
हाँ sir,
hello.
बताइए.
Sir, in the previous slide, yes. Sir, minimum and maximum. Why there is minimum and maximum?
Yes sir. Actually, the thing is for measuring each phase power, we need each wattmeter. For each phase, we need minimum for measurement of power. For each phase, we need separate wattmeters are required. That is maximum condition. But in minimum condition, with the help of single wattmeter itself, we can able to calculate the total power in a given 3-phase system. Okay. So the possibility we are discussing here, with the help of that means with the help of minimum resources, we are going to meet our requirement. That is called minimum condition. Maximum means actual requirement. Maximum means actual requirement for measurement of power. Minimum means with the available resources. We are having only single wattmeter. Even though we are having single wattmeter, we can measure the three-phase system in
But it
balanced
should be
condition.
balanced.
Yeah, then it is
Okay.
balanced. As
Okay, sir.
Kumar sir told in previous year question, they asked like this. That means if they didn't mention anything, we need to consider it as unbalanced. If they specifically mentioned three-phase balanced system, then the minimum wattmeters required is one number. Okay.
Okay, sir.
Okay, sir. Some important formulas are there, sir. Just remember, these are very, very important for our exam point of view. Wattmeter one, there are 2 meters we are using. If you see the table here, in both the table, either three-phase 4-wire system or three-phase 3-wire system, if your minimum wattmeters required is for unbalanced condition is 2. For unbalanced condition is 2. Okay. For unbalanced condition, minimum wattmeters required are 2. So in general, our system, most of our systems are unbalanced system only. We are going to prefer 2 wattmeters for measurement of power. 2 wattmeters for measurement of power. So we are going to do the calculations here. We are having 2 meters W1 and W2. The three-phase power formula is root 3 VL IL cos pi. Root 3 VL IL cos pi. Okay, where VL is line voltage, IL is line current, cos pi is power factor. Okay, so we need to get the root 3 VL IL cos pi by using W1 and W2. So W1 formula is VL IL cos 30 minus pi. W2 is VL IL cos 30 plus pi. Okay, so for getting power, three-phase power, what we need to do, if you add W1 plus W2, we will get this formula, root 3 VLIL cos pi. Okay, is it clear, sir? So for getting total power in unbalanced system is W1 plus W2. W1 is VLIL 30 minus pi, W2 is VLIL 30 plus pi. Okay, sir, this is called active power. This is called active power. What is meant by active power and reactive power? This also will study in networks only, sir. Okay, just for time being, active power means which the power, actual power we are going to utilize for conversion of output. Reactive power means for production of magnetic field, we need some extra power. That power is called reactive power. Wherever in electrical subject, wherever magnetic field is developed with the help of electrical energy, there we need reactive power. We just remember that concept. Okay. For time being, active power means actual power which is going to be contributing in the output. Reactive power means which is going to responsible for production of magnetic field in electrical devices. Okay, so this is reactive power is denoted by Q. Three-phase reactive power can be written as root 3 VL IL sin pi. Root 3 VL IL sin pi. Okay, if you do, for that what you need to do, W1 minus W2 if you do, we will get the reactive power. One more power factor formula is cos pi is equal, can be written as tan inverse root 3 W1 minus W2 by W1 plus W2. This formula is important, sir. You may get the question like this. That means by using 2 watt meter method, how we can calculate the power factor. By using 2 watt meter method, that means 1 watt meter will show W1, another watt meter will show W2. Okay. So from that we need to calculate the active power, reactive power, and power factor. Okay. These formulas are very, very important, sir. You may get a simple problems. You may get a simple problems from this concept. Active power, reactive power, and power factor. These three can be measured by using 2 watt meters in unbalanced system. Is it clear, sir? This is also very, very important table, sir. For our exam point of view, no need to by heart anything here. I just remember two formulas. W1 is equal to VLIL cos 30 minus pi. Cos 30 minus pi. Another one is W2 is equal to VLIL cos 30 plus pi. Cos 30 plus pi. You just remember these two formulas, then you can able to fill the table very easily. Many of the examinations, the questions are like this. In a three-phase system, by using 2 watt meter method, we are going to measure the power. That time, if 2 watt meters showing same reading, what is the power factor? What they are telling, if W1 is equal to W2, what is the power factor? The question will be like this. What is the power factor? Okay, what is the power factor means? That power factor is unity power factor. This question is very, very, very important. Many times it is repeated. And one more is this one. Okay, total table is important, but many examinations these are repeated. What they are telling, if W1 is equal to W2, what is the power factor? Just remember this formula. Make W1 equal to W2. What will come? Cos pi is equal to 1 will come. Okay, if you solve the equations, you will get the cos pi is 1. Or you can substitute the angle here. Okay, power unity power factor means 1. 1 means cos pi is 0. Sorry, cos pi is 1 means what is the pi? Pi is equal to 0 degrees. If you substitute this pi is equal to 0 here, we will get whether W1 equal to W2 are coming or not, we will see. Okay, so if the questions are coming like this, what we need to do? We need to calculate the pi. From the given condition, we need to calculate the pi. If you know the pi, you can substitute here, and thereby you can say the condition whether it is W1 equal to W2, or one of the wattmeter 0, or one of the wattmeter reading is equal to twice of the other meter. Okay, so these are the different power factors occurring in our electrical system. Okay, unity power factor. This is also called UPF. UPF. When cos pi is equal to 1 means that is called unity power factor condition. This is 0.86, 0.5, and this is power factor is 0. This called lagging power factor. Lagging power factor. You can say lagging power factor. Okay, when power factor is unity, what is the wattmeter's reading? W1 is equal to W2. If power factor is 0, then one of the wattmeter will show negative reading. Okay, this table is very, very important, sir. Just remember these formulas, and you need to substitute the angle pi. Okay, based on the given conditions, you need to calculate the pi, and you need to substitute here. Thereby, we will get the observations. Okay, for our exam point of view, this table is very, very important. Okay, just follow the methodology how to solve the given question very easily. Okay, next question is next concept is about energy
Sir, please
meter.
the table, sir. Sir, for 1 minute table, sir. Last slide.
Yes, sir.
Okay, done.
Okay, sir. Thank you. Okay, next topic is about energy meter. Energy meter. Okay, what is mean by energy meter means it is going to measure the electrical energy. Till now we discussed about a meter, that means measurement of current, measurement of voltage, measurement of power. Now we are going to measure the measurement of energy. In general, the electrical energy can be measured in the terms of kilowatt hour. Kilowatt hours. Okay, the units for electrical energy is kilowatt hour. Okay, in our home also we are having a one energy meter fixed by our local EB department. Okay, if you see our electricity bill is usually they will give in units. They will give in units. 1 unit is equal to 1 kilowatt hour. Okay, if you observe our electricity bill, in that they used to mention number of units consumed. Okay, number of units consumed means 1 unit is equal to 1 kilowatt hour. Okay, nowadays most of the EBs they are using digital energy meters, but in olden days this type of meters they used to use electromechanical energy meters. Now we are going to study about electromechanical energy meters. These are there in olden days. I think in still some EBs they are using this type. Nowadays all EBs replace the electromechanical with the digital meters. Okay, so what energy meter is going to do? It is going to measure the electrical energy in kilowatt hours. That means number of units. If this is the scale, in general, if you observe our meter in our house, there is some reading will be there. The numbers are continuously rotating. What that numbers indicating means, it is indicating the how many kilowatt hours consumed by the consumer. How many kilowatt hours consumed by the consumer. Okay, so for our exam point of view, these units are important. The electrical energy units are kilowatt hours. Power units are watts. Okay, voltage units are volts. Current units are amps. Coming to mechanical energy meter, it is also similar to watt meter. Whatever the principle here is, almost similar to watt meter, dynamometer principle only, with some constructional differences, small constructional differences. If you see here, this is called current coil, this is called pressure coil. So in our, if you see the connections, this current coil will carry the current. This can be written as kilowatt hour, can be written as V into I cos pi into 10 cube into T. 10 cube into T, where T in hours. T is in hours. That means this I going to measured by current coil, V is going to measured by pressure coil. Okay, so the current coil is responsible for the how much current is how much current is taken by the consumer. That's why if you see our meters, the EB department they are going to make the seal. Why they made seal means, if you bypass this meter, if you bypass this coil, what will happen? This meter won't show any reading. Okay, so this bypass connection will draw more current. Okay, this bypass will draw more current. No current will flow through the current coil. Thereby our meter will not show the accurate value. Okay, so in order to overcome this, what they are doing, they are making the seal on the meter. If you broken the seal means we need to pay the penalty for local EB department. Okay, what we need to remember for our exam point of view, current coil is responsible for measurement of current. Pressure coil, PC, is nothing but pressure coil. It is responsible for measurement of voltage. Now what will happen? This current, because of current flowing here, some magnetic field will develop pi 1. Because of the voltage of the given system, here also some magnetic field will develop. This field is called pi 2. Okay, when these two fluxes are there, This is going. This is aluminum disc. This is aluminum disc. What will do? It will exert a force on the aluminum disc, and the disc starts will rotate. Disc starts rotate. Once the disc starts rotate, the spindle will rotate. This is spindle. When disc rotates, spindle rotates. By using gear mechanism, these numbers also will change accordingly current consumption. Okay, accordingly our current consumption. Understood how energy meter is working? There are two coils are there. One is current coil, one is another is pressure coil. This current coil will develop flux. This flux is directly proportional to the current. This pressure coil will develop one flux I2. This flux is directly proportional to the supply voltage. Okay, because of these two fluxes, some force will develop, and this force, because of this force, the aluminum disc will starts rotating. Aluminum disc will starts rotating. Once the disc starts rotating, then with the help of gear mechanism, this numbers recording mechanism will record the reading. Recording mechanism will record the reading. Okay. For our exam point of view, one of the most important thing is brake magnet. This is very, very important. This is very, very important. What is the brake? What is the purpose of this magnet is? Let's take the distance is R. Distance is R. From aluminum disc to R is distance between aluminum disc to brake magnet. Disc to brake magnet. Brake magnet. If you bring the magnet towards the aluminum disc, the speed of the aluminum disc will increase. Whenever speed of the aluminum disc will increase means, even though you consumed less energy, the meter will show very high reading. The meter will show very high reading. Okay. If you bring the disc towards the aluminum disc, then speed will increase. If you take away from the aluminum disc, then speed will decrease. This is can be the relation is R is inversely proportional to N. N is the speed of aluminum disc. N is speed of aluminum disc. Aluminum disc. This is very, very important, sir. Many exams it is repeated. What is the how the question will come means, if brake magnet move towards the aluminum disc, then what is the speed of the disc? If you bring brake magnet towards the aluminum disc, the speed of the aluminum disc will increase. So we will note here. If brake magnet moves towards aluminum disc, speed will increase. If you take away, speed will decrease. This relation is important. Many exams this is repeated. Okay, so based on the brake magnet concept only. One more important is creeping error. One more important thing in energy meter is creeping error. What is creeping
Sir,
error means?
Sir, please show previous slide, sir.
Okay, sir.
Oh, okay, thank you, sir.
Okay, sir. What is creeping error means? Even though current in current coil is 0, even though current in CC is 0, aluminum disc will rotate slowly. Aluminum disc will rotate slowly. This is called creeping. and the error, and the corresponding error is called, and the corresponding error is called creeping error. Corresponding error is called creeping error. Okay, what it indicates means, if you see the diagram here, for rotation of this aluminum disc, main portion is CC only. Main portion is CC. This is the playing major role. Okay, so the energy meter reading mainly depends on the current consumed. Okay, why current consumed means voltage is constant in our system. Voltage is constant. Only variable one is current. Okay, so if you are using more number of loads in our home, the load current will be high. Based on that, the rotation of the disc also will increase. Okay, so that's why the energy meter reading mainly depends on the current coil only. Okay, but in some case what is happening, even though current coil is carrying no current, that means I is equal to 0, still the aluminum disc is slowly rotating in the meter. Why it is rotating means because of the over friction compensation. Actually, if you see here, actually whenever moving arrangement is there, actually this is the spindle is moving in the meter. Okay, here some friction will occur. To minimize that friction, what they are doing some friction, some lubrication they are doing. Sorry. To minimize the friction, here if you observe here, to minimize the friction, lubrication they are doing, lubrication used. Okay, and in moving parts they are going to use the lubrication. So that's why, because of if over lubrication they applied means, what will happen, the aluminum disc will rotate slowly. Okay, aluminum disc rotate slowly. One more is, if over voltage, normally voltage is constant, if over voltage is occurring in our system, then also the aluminum disc starts slowly rotating. That slowly rotating process is called creeping, and whatever the error is occurring due to this process is called creeping error. Bala sir,
Sir,
any doubt? Okay. Okay, so the reasons, if you see, these are important, sir. Our exam, many of the questions are repeated on this concept. Okay, reasons for creeping. What are the different reasons? Are, first one is over friction compensation. The second one is over voltage condition. How to overcome this creeping error means, if you see the aluminum disc like this, how we are going to overcome means, they are going to drill the two holes in opposite direction. Okay, these are the holes. This is aluminum disc. To overcome creeping error, what they did on the aluminum disc, they made two holes. They drilled the two holes. Why they made it holes means, whenever holes are there, their reluctance is high. Okay, because of these holes, reluctance will increase. Reluctance means flux decrease. Flux decrease means speed will decrease. Okay, by making two holes in the aluminum disc, they are going to reduce the speed. Why? How reduce means, whenever we are having air gaps, their reluctance will be more. Reluctance 4 means flux will decrease. Flux decrease means speed of the disc is going to be decreased. One more method is this is first method. One more method is first method remedies, you can say remedies. What are the remedies? Drilling holes in aluminum disc, holes in aluminum disc. This is first method. Second method is adding small iron piece to the disc. What will happen if you add any small iron piece to the disc? If you see here, if you add a small iron piece, what will happen? This is the iron piece. Let's take this is the iron piece. After half rotation, what will happen? Whenever it is coming under the magnetic brake magnet region, this magnet will attract that iron piece. Thereby, the rotation will get stopped. Okay, is it understood? So first method is they are drilling 2 holes in the aluminum disc. That is first method. Along with that, they are going to attach small iron piece. Okay, because of this iron piece, whenever this iron piece will come nearer to the brake magnet, this brake magnet will attract the iron piece. Thereby, it is going to stop the rotation. Okay, this is called creeping error. This is very important related to energy meter, sir. Many of the questions are coming like this. Okay, in energy meter, aluminum disc is drilled holes to reduce friction losses, core losses, iron losses, and creeping error. Okay, the most important question in energy meter concept is creeping error. To minimize this creeping error, we are going to drill holes on the aluminum disc, and second one is we are going to attach small iron piece on the aluminum disc such that the speed of the disc is going to be reduced. Okay, one more important formula related to energy meter is energy meter constant. K is given as number of revolutions divided by number of revolutions divided by kilowatt hour. Actually, this is important for solving the problems. Okay, we'll solve 1 or 2 problems, so we'll understood how the questions will come from the energy meter. Okay, they will give number of revolutions and they will give the energy constant, and they will ask to find out something. Okay, let's frame a question. We'll frame ourselves. Oh, no problem. A 230 volts, 10 amps, 0.8 load is connected to 0.8 power 0.8 lagging load is connected to a energy meter with a meter constant of 1000. Then number of revolutions of meters are number of revolutions of meter are. Okay, just I framed one small question. Most of the exams they used to ask simple questions like this. Okay, they given the meter constant K is given as 1000, and the whatever the first thing while solving problems is first note down the given data. First is voltage given 230 volts and current given 10 amps. Power factor given cos pi is 0.8, meter constant 1000. They are asking n number of revolutions. They are asking number of revolutions. Okay, so we know that meter constant K is equal to N by kilowatt hour. Okay, N by kilowatt hour. We know K, and if you were able to calculate kilowatt hour, then you can calculate speed. Okay, 10 amp is calculated for 10 hours. For 10 hours, let's take 10 hours, and time also given 10 hours. Okay, now we need to calculate kilowatt hour. Kilowatt hour is equal to normal. What is mean by kilowatt hour? Kilowatt hour is VI cos pi into 10 cube. Whenever kilo coming means we need to multiply with 10 cube into T. Just substitute 230 into 10 into cos pi is 0.8, 10 cube into T is for 10 hours. T is for 10 hours. How much it will come? I start like this. Actually, the formula you can write as VI cos pi divided by 10 cube into T. Okay, we need to convert the watts into kilowatts. That means we need to divide the 10 cube there. Okay, we need to divide the 10 cube into T. Okay, so 194 will come, and it will answer is it's 1.84 kilowatt hour will come. Okay, so the given K as 1000 and N we don't know. 1.84 we know. That means we can get N is equal to 1840 revolutions. N is equal to 1840 revolutions. Okay. Mostly you won't get any problems. In case if any problem coming means in the energy meter, the problems will be like this only. They will give voltage, current, power factor, and they will give the power. One more question like this. They will give the number of revolutions, and they will ask the meter constant. Okay, they will ask the meter constant. You just remember the formulas. Okay, if you know the formulas, you can solve the question very easily. Okay.
Sir, in place of lagging, if you give a leading, then what?
Leading
Power
also
factor.
no sir, no difference sir, especially in energy meter, whether it is leading or lagging, no difference sir.
Okay, okay.
Okay sir, any doubts sir? Okay, by that
Till
we
now we have
completed
no doubt.
okay sir, thank you sir. By that we completed the energy meter concept. Okay, so I just
Sir, sir, one more.
sir,
Sir,
बताइए sir.
our home load is what, sir? Lagging, sir.
सर ये लीडिंग लैगिंग क्या होता है ना सर? Actually leading lagging concept is like this. Okay, wherever you are
अरे झाड़ू सामने मारना चाहिए, तो मतलब आपका तो दिमाग भी उल्टा चलता है।
अभी गंदा लग रहा है, सामने मारने से सामने साफ था।
सब में सब।
सर, कुमार सर आप थोड़ा म्यूट कर सकते हैं सर. ओके, अभी लीडिंग लैगिंग मीन्स main thing is just remember wherever magnetic energy conversion is involved, there the power factor will be lagging. Just remember simple concept. Wherever magnetic energy concept is involved in our any electrical apparatus, any electrical appliances, there the power factor will be lagging only. Okay. To overcome that, we are going to connect the capacitors. Wherever capacitors if you see, okay, wherever capacitors if you see, that is leading load. That is leading load. In most of our house appliances are lagging loads only. If you take any load, that means tube light nowadays LED came. Before that electronic chokes, before that ballast was there. Okay, wherever ballast was there, and fans, if you see, ceiling fans, table fans, and even air conditioners also. Okay, air conditioners, all these are lagging loads. Okay, wherever magnetic energy conversion is involved, those all are lagging loads. That is first point. Second point is wherever power electronic converters are using. That means electronic circuits, wherever electronic circuits are using, there also that lagging load is occurring. Okay, so if you see overall loads in our home, that is mostly lagging load only.
Okay, sir.
Okay, sir. Thank you. Any doubts?
Sir, last time ஒரு கொஸ்டின் வந்திருந்தது சார், எலக்ட்ரிக் பல்ப் இஸ் லீடிங் பவர் ஃபேக்டர் ஆர் லாகிங் பவர் ஃபேக்டர் சார்?
Okay, sir. Actually, bulb means the பார்த்தாச்சுன்னா இதுக்கு முன்னாடி இன்கேண்டசென்ட் பல்ப் இருந்துச்சு சார்.
சார்
நம்ம ஓல்டன் டேஸ்ல, if you see in olden days, round bulb, incandescent bulb was there. That is only resistive load, sir. When that is resistive load, or wherever one more thing I will explain, sir, in simple. If you are telling in parameters, there are networks, 3 parameters are there: R, L, C. Okay, if you see the bulb, incandescent bulb, we can going to represent it as resistive element. The bulb is going to be replaced in our circuit as resistance. For resistance, power factor is UPF, unity power factor. Okay, so if the question is about tube light, electronic choke tube light, there L will come. If you see the electronic choke tube light, this is a choke tube light. If you are using choke tube light, there will be more inductance will be there, then it is lagging load. Okay, then it is lagging load. For capacitive loads, the best example you can say, which one you can see capacity load. In our house, our home appliances, we are not using capacity load, sir. But
Fan,
in
sir?
industry,
Fan,
sir?
sir? Fan
Fan also lagging only, sir. Fan also, inside that the coil will be there, no, sir. The magnetic energy conversion is occurring. So in simple, just remember, sir, wherever magnetic conversion is happening and wherever electronic circuits are there, that load is always lagging load, sir.
Okay, sir.
Wherever we are able to quantify as pure resistive load. Pure resistive loads are incandescent light, incandescent bulb is there. One more is heater, geyser. All these are resistive loads, sir. So the power factor is about, sorry, not geyser, only heater, sir. Geyser again it will come in lagging power factor. Nowadays, whatever geysers you are using in our home appliances, those are lagging power factor. Heater means coil type heater, I am telling. The structure will be like this. If you might have seen the heater, okay, this type of heater is coming under resistive load. So that is UPF. Wherever capacitance involved, that is leading load. Bala sir, நீங்க எப்படி வந்துச்சு சார் கொஸ்டின், எந்த மார்க் கேட்டிருக்காங்க
சார்? அது மறந்துருச்சு சார். ஆனா வந்துட்டு பல்பு, எலக்ட்ரிக் பல்பு பவர் ஃபேக்டர்னு சொல்லி ஒரு 4 இது இருந்துச்சு சார். லீடிங், லாகிங், யூனிட்டி, அந்த மாதிரி ஒரு கொஸ்டின் இருந்துச்சு சார்.
ஓகே ஓகே சார்.
Actually, normal bulb, sir. That is normal bulb.
நார்மல் பல்ப். அப்போ அது நார்மல் பல்ப்னா, if it is
Unity power factor.
yeah, unity power factor, sir, UPF, sir.
Okay.
So you need to consider as a bulb. Normal bulb means incandescent bulb or LED bulb. If they are mentioning tube light specifically, it is lagging loads.
Okay. Okay, sir.
Okay, sir. Okay, okay, sir. Thank you, sir.
Thank you, sir.
Good night.
Thank you, sir. Good night, sir.
Sir, Brizlal, sir, any doubt? Okay, he left. Okay, okay, sir. Thank you.